Welcome to the first video to practice for the OGT science test coming up the week of March 13th. We're starting with physical science questions, and today we're going to look at questions dealing with motion and energy. So here's our first question. This is: a student records the position of a car every second for a period of time and plots the following displacement and time graph. Displacement is kind of a fancy science name for distance, so it's distance and time. And notice, though, the graph is a straight line. You remember from your math, straight line graphs have a constant slope. So that means this distance over time is causing a speed, which is a constant speed. So we're supposed to take a look at A, B, C, and D, and these illustrations of the change in position of a car every second, and which of these dot plots then would the student record? Remember, constant speed. So the only one of these dot plots that has the same distance between their dots all the time is plot A. So that's the only one showing constant speed. But kind of like if a strobe light was on and you could see the position of the car every time the strobe went off. So it's point A because of the smooth line, and then the same amount of distance every time you look at your points. Number 32. This was from March 2009. It says light travels in air at approximately 3 times 10 to the 8th meters per second. When it enters a glass window, the speed is reduced to about 2 times 10 to the 8th meters per second. When the light re-enters the air, what will be the speed of, when the light re-enters the air, what will the speed of light be? I think you may have talked about this. It's that refraction. Say we draw, this will be our thickness of our pane of glass. We've got light coming in. Then when it hits the glass, it slows down a little bit so that it changes a little bit of direction, a little bit. But then when it comes out, it should be traveling parallel to the way it came in. So since it's in air here and in air here, its speed is the same. So coming in, it was this much. So coming out, it will be that much as well. And there's really no calculation you could do anyway to come up with a different answer. Okay, so there you go. That's that refraction slowing down, but air on the outside, air over on this side would be the same speed. Oh, I'm sorry. I did want to mention one more thing, too. Light travels better without a boundary. You know that. If you put a door in front of you and something, you can't see through the door. But sound, however, does travel better with boundaries. It travels better through solid objects, actually, than it does through air. Speaking of speed of sound, here's our next question. And here we have a table. The speed of sound in dry air. Now, dry air means there's not very much humidity, and of course, it's not raining. So here's the temperature, 0, 25, 100. That's in Celsius. This is freezing water. This is boiling water. And then this is a little warm for room temperature. But here's the speed of sound. You can see it's going up a little bit. So the question says, could the speed of sound be used to estimate dry air temperature based on the data? And question A, or part A, says no, because the speed of sound in dry air is the same regardless of temperature. That is not true. We see this going up. B, no, because as temperature increases, the speed of sound in dry air increases. It's true. As temperature increases, the speed increases, so I don't see why that would be a no. I think that's the yes. And C, yes, because as temperature increases, the speed of sound in dry air increases. So that would be the yes. It can't be D, because it says as temperature decreases, the sound increases, and that's not true. They're both increasing at the same time. So that would mean you could use this chart to estimate the time. A driver is headed north at 50 kilometers per hour. A box is sitting on the seat next to him. Here's the driver, here's his box. What action by the driver would most likely cause him to observe the box appear to slide to the west? Which is this way. In this case, it's to the left. Can we apply the brakes, speed up to 60, make a turn to the east, or make a turn to the west? This reminds me of Newton's third law. That third law was the equal and opposite reaction law. Equal and opposite. So if the driver, we want we want the box to slide to the west. So if we want the box to go this way, that means the opposite thing would be for the driver to turn to the east. And you know, if he put on his brakes, especially if you put the brakes on fast, the box would go forward. Okay, so this is that equal and opposite of Newton's third law. So we're going to turn in the opposite direction to get the box to slide. We have two questions here. Jackie is using a portable electric drill to remove screws from a broken wooden table. He noticed that the screws holding the table together were warm to the touch after being removed from the wood. What explains this phenomenon? Mechanical energy from the drill was converted into thermal energy due to friction. Now, do we know thermal energy? Anytime you see the word thermal, you think of heat. Like a thermos. Thermoses were originally made to keep coffee hot. Then, of course, they can branch out to keep things cold as well. But thermal refers to heat. It says electrical energy from the drill was converted to chemical energy due to resistance. Thermal energy from the drill was converted into mechanical energy due to inertia. The process of removing the screw concentrated the thermal energy that was already present in the wood. Okay, so we don't want to make this too hard because actually a lot of these are kind of common sense. And they did try to fool you a little bit by using a portable electric drill. But we don't really care that the drill was electric because what's happening here is the mechanical part is the drill bit going round and round and round into the wood. So that's mechanical energy, energy of motion. It's moving. So it is A. Mechanical energy from the drill is converted to thermal energy or to heat up the screws. So this is actually the only one that talks about converting into thermal, and that's what happens when they get warm. Although D says the process of removing the screws concentrated the thermal energy that was already present. That might be a distractor that you might think of. But it's mechanical energy from the drill bit moving in a circular pattern there. So they try to fool you with this electrical energy, I think. But again, that went to chemical. It has to go to thermal because it got warm. So our correct answer is A. Another question here. A student walks from inside an air-conditioned building to stand outside on a sunny, sandy beach. The student says that her face and the bottoms of her feet feel warm. Which statement best describes the thermal energy transfer taking place? So again, it's about heat. So they talk about thermal energy transferred to her face by radiation and thermal energy transferred to the bottoms of her feet by radiation. So now radiant energy is energy from the sun, a source like the sun, or from a heat lamp, one of those tanning beds. That would be radiant energy. But the bottoms of her feet are not getting the radiant energy because it's blocking. Her feet are blocking the radiant energy from touching her. So that can't be it. Thermal energy is transferred to her face by convection. That's not true because her face is facing the sun, which is giving out radiant energy. Convection is energy that travels on movements through fluids, like through liquids and gases. Like in your oven, some people have convection ovens now at home, and convection also is found in the ocean a lot, where the warm currents move around. And it says thermal energy. This says the bottoms of feet by radiation again. We said no. We said bottoms of the feet are not radiation. Okay, but we did say her face was radiation. But this says face convection, so B's way out. This says face by radiation, that's right. And it says thermal energy transferred to the bottoms of her feet by conduction. And that would be the correct answer. Conduction is where heat is transferred through touch. The bottoms of her feet are touching the hot sand. So that's a conduction going on. So it's got to be C. Let's see why it's not D. D says thermal energy transferred to her face by conduction. That would mean the sun is sitting on her face. I don't think that could possibly happen. So the correct answer is C. So again, you have to know the difference between radiation, conduction, radiation, and convection. I guess I already crossed off the word convection. But those are the three you have to know. Radiation is radiant energy from a heat source like the sun or strong bulbs. Convection are currents that flow through fluids. Fluids are gases and liquids. Conduction is by touch. You know, it's like pans. You can buy some pans have those nice handles that are made of silicone or whatever, so that you're not really touching the metal. But if the pan has metal handles, you're going to have to use pot holders or something. Otherwise, you're going to get burned from conduction. Okay, number 26. This is going to be talking about potential energy here. It says, all carts shown below are identical 0.5 kilogram metal carts. Blocks placed in the carts have a mass of 1 kilogram each. So we see this is an empty cart. This has got 2 blocks, 1 block, and this one's got 1 block. But it says, which cart arrangement has the greatest amount of gravitational potential energy with the cart sitting at the top of the ramp? Now, please notice this, because you might not have noticed right away. This ramp is 2 units high. This ramp is 3 units high, also 3 units high, and only 1 unit high. Gravitational potential energy. Potential energy has a formula, mgh, where m stands for mass. G is the acceleration due to gravity. So we can't change the acceleration due to gravity. That's the same on the surface of the Earth all the time. So that's not going to influence our decision. What's going to influence our decision is the mass of the carts and the height. So we got to find the one with the most mass and the most height. And luckily, we don't have to make a real hard choice, because this one has the maximum height and the maximum weight. So B has to be the cart with the most gravitational potential energy. And potential energy is energy of position. Think of it that way. Position, height. It's got to be up high to have potential energy of position there. This one here from March 2008, it says W reacts with X in this equation below. W reacts with X and you get Y and Z. According to the law of conservation of mass, that means mass is neither created nor destroyed. It remains the same. They also talk about there's a conservation of energy as well, but we're talking about conservation of mass. So it says how many grams of W must react completely with 225 grams of X to result in 375 grams of product. So the product is this over here. So this together is 375 grams of mass. On this side, we don't know what W was, but X was 225. So remember, conservation of mass. This side has to equal that side. So what do we add to 225 to make 375? Is it 150, 225, 375, or 600? It happens to be 150. 225 plus 150 gives us the 375 that's equal to the product on the other side. So that's what they mean by conservation of mass. Mass before the reaction has to be the same as that after. This is a good illustration for some of the short answer problems that might be coming up soon. Here's a picture of a person walking on a flat surface. And the person is going forward. It says, which statement accurately describes the interaction between the foot and the sidewalk as a person moves forward along the sidewalk in the direction of the arrow? Again, this is Newton's third law. This is that equal and opposite. So it has to be equal and opposite. It says the foot pushes forward on the sidewalk does not push forward. That's not true. There's got to be an equal and opposite force. The foot pushes forward on the sidewalk pushes forward on the foot. That's two forwards. Opposite of forward would be backwards, so it's not that. C, the foot pushes backward on the sidewalk pushes forward on the foot. That's starting to sound good. D, the foot pushes backward on the sidewalk pushes backward. Nope, again, two backwards. It's got to be C, that equal and opposite from Newton's third law. Opposing forces. So that reminds me of this picture here coming up. It's a 2-point problem. You have a sailboat moving at a constant velocity of 8 kilometers per hour eastward, as shown in the picture. Describe two opposing forces acting on the boat and explain how each force affects the boat. So I've already I've typed this out neatly so that I don't have to write and so that you can try to read it. Here we go. And there's really not a whole lot of choice in this problem. Sometimes you have more choice when you answer, But there's basically the opposing forces would be the wind on the sail that moves the boat forward, so the wind pushing on the sail, and the friction caused by the water. So the boat has to cut through the water, so the water is causing friction that reduces the forward motion. So it still gets to move forward because the forward force is greater than the force of the water holding it back. But those would be your two opposing forces. The wind on the sail propelling you forward, and the friction causing the boat to go a little bit backward. Which reminds me, I forgot to mention at the beginning, if you could have downloaded the packet that goes with this video, then you have all these and the answer document at the end of the packet so that you can check your work. And you can also follow along better with the next videos that we have. The picture below shows the different positions of a skier as she is lifted to the top of a slope and then skis down the other side. Which statement best explains the change in the skier's potential energy? We talked about potential already. MGH is potential energy. G again is the gravitational force the force of gravity, which you cannot change at the surface of the earth. And in this case, we can't change mass either, because the mass of the skier is not changing. So the only thing that changes is the height. So the more height, the more energy. The less height, the less energy. So let's see which one says that. The skier loses potential energy as she is lifted up. No, as you're going up higher, you are getting more potential. That's not right. The skier gains potential energy as she's lifted up the slope. Yep. And maintains the same as she skis down. Nope. She gains up here, but she's losing potential when she comes down. That's not true. By the way, she's not losing energy. It's just that when she's skiing, the potential energy is changing back to kinetic. But she is losing potential energy. She just happens to be gaining kinetic. C, the skier gains potential energy as she's lifted up the slope and loses as she skis down. I do believe that's correct. Let's double check D. The skier loses as she's lifted up. Nope, can't be that. It's got to be C. She gains potential going up, making the height higher, loses as her height gets lower again. We have another one of these energy transfer problems. Which energy transformation below describes the conversion involved when carbon compounds in wood are burned? So if you burn wood, you're going to give off heat. Heat is what we call thermal energy. So we're expecting something in the thermal category here. And as I look through these answers, I only see one that mentions thermal. Chemical energy, that's the energy in the compounds that are in the wood, is converted to thermal. I believe that's correct. Because B would be backwards. You're not converting thermal to chemical because you're giving off the heat when it's burned. Potential energy is converted into chemical. No, it has to be thermal energy given off. And it says chemical energy is converted into potential. Again, these two are opposites, but it's not true. A is your correct answer. You're getting thermal energy. So if in doubt, it's usually the simplest one. Fire is heat. Heat is thermal energy being given off. Here's another illustration of different kinds of forces. This shows 4 major forces acting on this airplane. There's lift from air. There's this force pulling you down. There's thrust moving you forward, and drag pushing you backward. The force indicated by X, that would be, of course, gravity. Gravity, you see it over and over again. Gravity is the force pulling you down, straight down toward the earth. It's not air friction. Air friction actually causes drag. It's not magnetic force, or it's not force exerted by the engine. That would be the force thrusting you forward. So gravity is pulling you down toward the earth. Got a couple questions about the little lemonade experiment. On a humid summer day, Franklin put 6 ice cubes into each of 2 cups and then poured the same amount of lemonade into each cup. They each got 6 cubes. They each got the same amount of lemonade. Cup A was made of plastic. Cup B was made of glass. He left the cups for about 20 minutes and then came back. He found a small puddle of water around cup A and a larger puddle around cup B. Franklin determined that the cups were not leaking. That's a good thing to include. Okay, sometimes at home people use coasters so we don't get puddles of water on our furniture. Which is the best explanation for the small puddle around A and the larger puddle around B? A, it says cup A contained more ice. No, they said they both got 6 cubes. So that's really a bad answer. You can get rid of that right away. Cup A was a better insulator. That's what I'm thinking. Cup A was able to keep the cold in longer. Cup A had a greater volume of lemonade. Again, that's a bad answer to pick because they said they both got the same amount. The contents of A were initially colder than the contents of B. I don't see how that's possible because they put 6 ice cubes into each and poured the same amount of lemonade. I assume the lemonade came from the same pitcher. But anyway, they're talking about insulators here. So the plastic cup is a better insulator than glass. So it has what they call it sweat, but it's actually condensation caused by the humid air on the outside condensing on the colder glass. So better insulator will prevent that. They have some of these insulators now, those Yeti cups, that I guess you can't even tell what's in them when you touch them on the outside. You can't tell if there's a hot liquid in there or cold. They're very, very good insulators. So you get no puddles of water around some of those insulated cups these days. Suppose Franklin had a third cup made of styrofoam, to which he added the same number of ice cubes and the same amount of lemonade. What would Franklin expect to observe after 20 minutes? So this is a little bit of common sense, I guess. You have to have lived around. So styrofoam, you see people a lot of times drinking coffee out of styrofoam cups because it prevents their hands from getting hot. So styrofoam is a good insulator. So I imagine styrofoam is going to be a better insulator than plastic. There's that, I don't know if it's a 7-Eleven or somebody on TV advertises their Big Gulp or something cup that it says that you can go all day and not have all your ice melt or whatever. So, and those cups are made of, I believe, styrofoam. So since the styrofoam's a better insulator, it would have a smaller puddle than either the glass or the plastic. It would have a smaller puddle. This one says it would be larger. This says exactly the same size. And this says it would be between the bigger than plastic but smaller than glass. But styrofoam would be your best insulator. So I hope you've seen that from experience sometime in your life. Here we have a graph. This is about different kinds of energy transformation. This is from states of matter. And that would mean your solid, your liquid, and your gas. So this is an example of the change in the sample of water, which technically begins as ice as thermal energy is added. So down here we have ice below the freezing point. So the ice is being heated up to 0, which is its melting point, or freezing. But since we're going in this direction, our frozen ice is going to start to melt. So here, while it's melting, it doesn't change temperature, if you recall that. So that's your plateau or flat spot on your graph. So this is melting ice. Now this is water. This is water that's being heated up. This is water that's boiling into steam. This is steam that's being heated. So which region of the graph represents water in the liquid form only? This could be ice and water. This could be water and steam. This section of the graph is the only one that's pure water. It's just water being heated. So that would be C. Remember, the flat parts of the graph are where you're changing from one to the other. So it's a little bit of a mixture there. A student plans to collect data needed to calculate the kinetic energy of a thrown baseball. She plans to measure the distance from pitcher to catcher. So she's measuring distance from pitcher to catcher. She's measuring the time it takes for the baseball to arrive. She's looking at the mass of the baseball, and she's looking at the circumference of the baseball. Which of these there's 4 of them. Which of these is not needed? Well, we need to know what kinetic energy is, folks. The formula for kinetic energy is 1/2 mv squared. So we need mass and velocity to calculate kinetic energy. None of these measured velocity, though. But if you recall, velocity is distance over time. So since she didn't measure velocity, we need distance, we need time, and we need mass. So distance from pitcher to catcher is how far she's thrown it. We need that. The time it takes for the baseball to get to the glove, that's the time it takes to go across that distance. The mass of the baseball that's thrown. The circumference of the baseball is not necessary. We really don't need to know how large the baseball was, just its mass. So measuring the circumference of the ball isn't going to help us calculate our kinetic energy. So you do have to have an idea of that kinetic energy formula. So you saw the formula for kinetic today and also for potential. A teacher dropped one light ball and one heavy ball simultaneously from the roof of a school building. Both balls struck the ground at the same time. So maybe one might be made of like cork or something, and one could have been made of maybe a metal, a copper or something. It says the students correctly concluded from this experiment that falling objects lose mass. Okay, they never said anything about measuring the mass before and after, so I don't think we can conclude that from here. Are influenced by the height. It didn't mention dropping it from different heights. They dropped it from one height, the top of the school building, so we don't know that for sure. Do not accelerate under the influence of gravity. Actually, things do accelerate under the influence of gravity. But here we go. Accelerate at the same rate regardless of mass. So this is what's important. It mentions regardless of mass because one was light and one was heavy. And so it didn't matter what their mass was. They hit the ground at the same time. So that would mean they had to accelerate at the same rate. And that's due to the force of gravity. And I mentioned that earlier in one of those formulas, that we cannot change that force of gravity at the surface of the Earth. Okay. We have a snowboarder beginning his run from rest up there at the top. He moves straight down the slope until he reaches the bottom of the hill at point 4, and the ground then levels off. And he continues to move horizontally across the level ground, and eventually will come to a stop. Okay. Using the same board, the snowboarder decides to make another run down the hill to see if he can increase his speed. Describe one thing the snowboarder could do to increase his speed on the slope. Explain why this would cause his speed to increase. Okay, now be careful, because you can't make assumptions. I do not think that we're going to be able to change the height of the hill. We're not going to be able to change the mass of the snowboarder himself. So I've seen that some students come up with those kind of explanations, but that's not much of a possibility. So I came up with a couple ideas here. If the snowboarder waxed the bottom of his board, that would reduce the friction force between the board and the snow. So his acceleration down the slope would be greater. So imagine if he put sandpaper on the bottom of his board. I think that would slow him down, much the same way waxing the bottom might speed him up. Another possibility is if he could crouch down lower. You've seen that maybe if you've watched any of those skiing competitions for speed on television. The lower the skier, they get a boost of energy because that's less air resistance on their bodies. So if he crouched down a little lower, he would reduce air resistance, which might give him a little bit better acceleration. Because air resistance would give him a net force that would be greater than without air resistance than with air resistance. So those are two ideas I came up with for the snowboarder to try to increase his speed. That's a 2-point question. And you don't have to have both ideas. I just threw 2 ideas out there. If you had one idea and explained it, then you would get 2 points. Which of these graphs best represents the speed of the snowboarder as he moves from 2 to 3? So is his speed staying the same? Is his speed going up? Is his speed going down? And this is an interesting graph where it looks like the speed is changing. Now he's going down an inclined plane. So as he's going down the inclined plane, his speed really shouldn't be changing. His speed should just be going up uniformly. because he's getting some acceleration from the force coming down. So this would be the graph you need. The speed being increased uniformly, which means constant acceleration. So the correct answer here would be B. So again, if in doubt, try to keep it simple. It's not this fancy curve, it's that straight line showing that the speed is going up. We have an inclined plane experiment. And in doing this inclined plane experiment in ideal conditions, students assume that friction from the incline or floor is negligible. A stationary box at the top of a frictionless incline is released and allowed to slide to the bottom. I don't know what released was. Anyway, it's released from the top of the incline and allowed to slide to the bottom. The figure below illustrates the box in 4 positions labeled A through D as it's sliding through the incline onto the level floor. As the box moves from the bottom of the incline to the floor, students assume that the box experiences no change in speed, only a change in direction. So instead of coming down, now you're going this way. When do we have the greatest kinetic energy? Remember, kinetic energy is mv, or 1/2 mv squared. The mass of the box does not change as it goes through the incline. So that has nothing to do with our kinetic energy. It's all about the velocity or the speed. So the greatest kinetic energy then would be after it's gone through all the incline coming back down now. So at part D, which is 1.25 seconds, that's when it has its greatest speed coming off the incline. Now the total energy of the box is always the same. So he has kinetic energy down here and pretty much no potential. But at the top, this is all potential energy. So that's what happens as the box comes down the hill. It's losing potential and gaining kinetic. The most potential, the most kinetic. So the total energy is always the same. It's just made up of 2 different types, kinetic and potential. Oh, they want to, next question. They want to know where the potential energy of the box is the greatest. We already mentioned that. It's at the top, which is point A. And it says that the potential energy is greatest at the top. They didn't actually say at point A or at that time. You just have to read through. It's at the top. Number 6 says, assume that the experiment will be repeated in less ideal conditions, where the effects of friction on the motion of the box cannot be ignored. Predict the effect that significant friction would have on the acceleration of the box as it slides down the incline. Explain the cause of the predicted effect. And that's another 2-pointer. So they said they assumed when they started this, like there's no friction. Like if this surface was made of ice, that would be very much almost frictionless. It would go slide down there. But if that was made of sandpaper, the box might have a hard time coming down the hill. So I've made an answer for this. It says friction would cause the box to accelerate less, so the velocity would not increase as much if there were no friction, as if there were no friction. Friction opposes the motion of the box down the incline, so the net force pulling the box down is less, which causes less acceleration. So we have a force pulling the box down the incline, but friction is pushing against that force. So if there's friction, you're not going to be able to accelerate as fast. And I want you to also recall that formula, F equals ma. Force on a mass causes acceleration. The mass of the box doesn't change, but since the friction force reduces your net, your acceleration is less. So it does matter whether you have friction or not. We do have another question based on this incline. It says the weight of the box used in the experiment is 10 newtons, as indicated in the figure. So if you need to look again, they did mention that the weight was 10 newtons on the box. And notice, weight is a measure of the force of gravity coming straight down. And that's what the answer is. The weight of the box is a measure of the force acting on the box due to gravity. So that's why they say you weigh less on the moon, because the moon has different gravity, less gravity than the Earth. So that's what weight is. That's really important to know. It's the force of gravity on your mass. And some people actually use that formula, F equals mg, to describe weight, because the acceleration is actually that of gravity. So that's another description for weight. Weight is a force. Hang in there, just a couple more. Okay, 2 more questions, and then this video is going to be finished. When dropped from the same height, why does a flat sheet of paper fall more slowly than the same sheet when it is tightly crumpled into a ball? Okay, I think you've seen this. I haven't seen a student yet try to make a basket in my classroom with a flat sheet of paper. They always try to crumple it up real good and then, throw high and soft to get a basket. So why is that, though? Why is the paper tend to fall more slowly? A lot of times, too, it even waves through the air as it's falling down. And the reason is, it doesn't have less mass when it's flat than it does when it's crumpled. It's the same sheet of paper. So it doesn't weigh less when it's flat and when it's crumpled. It's got the same mass, and it's under the same amount of gravity. But so it's not gravity, because the force of gravity is the same. Here it is. It's that air resistance. There's a lot more air resistance on a flat sheet of paper than on one that's crumpled. And you've seen that for skydivers, too. Skydivers try to spread themselves out so that they're falling more slowly at first, and they can dive down if they want to go down faster. So air resistance is the reason that the flat sheet falls more slowly. It's not because it weighs more or less, etc. It's air resistance. Number 25, our last question for physical science, motion and energy. When a space shuttle is launched, it continues to accelerate for several minutes. Which graph shows the kinetic energy of the space shuttle during the first few minutes of flight? So kinetic energy, again, is 1/2 mv squared. Okay? I suppose the mass of the space shuttle might go down a little bit because as fuel is ejected. So the mass may change a little bit as well. But most of our kinetic energy is from our velocity. So if we're accelerating, that means our velocity is changing. Acceleration is a change in velocity over time. So that means the kinetic energy has to be going up. Speed's going up. So the one that shows kinetic energy going up, not this one, shows it the same. Here shows it going down. This one is going up. It's got that unusual pattern, though. It's not this, because this is going up and then coming back down, because we're only talking about the first few minutes, and it said that it continues to accelerate for several minutes. So if it's accelerating, kinetic energy is increasing, which is graph A. So once again, if you haven't yet, I urge you to download your own packet of questions. You can redo them, check your answers at the back. And our next video is going to be on physical science, the elements and their properties. So hope to see you soon. Hope you're studying. Bye for now.